Thanks, Adam. So I enjoyed meeting you guys yesterday. I didn't get a chance to meet everybody. So just to introduce myself, I'm a postdoc working with the LSST Data Management Group on science pipelines. And before this, I was a grad student at the University of Washington in astronomy. But before that, I worked for a consulting firm doing data management for the private sector. So we did data management for federal investigations and e-discovery. We did data management for bankruptcy cases, and I just started. And we also did the general predictive analytics for business performance improvement that you think of when you usually think consulting. So I've seen a lot of databases, both in industry and astronomy. And I know there's a lot of options and a lot of tools out there. And I was hoping to demystify all the different tools that are out there and discuss what trade-offs you should consider when deciding how to manage your data, and also some tips for accessing large databases that are made available by surveys such as the SDSS and LSST in the future. Why are we spending why are we spending a couple sessions in this week about data management? Not only are data sets in astronomy getting bigger, but project teams are getting bigger too, and we have to think more carefully about sharing. Also, you could break down data science into 3 primary steps. There's prepping to run your model, there is actually running your model, that's choosing and evaluating different ways to model your data, and then there's communicating your results. And my understanding is that you guys are going to be learning all of that over the courses of these sessions. The second step is by far the most fun. It's the one where you get to actually use all your knowledge to learn something new about the universe that nobody else knows. But it also is probably where you spend the least of your time. You probably spend a lot of time handling data, and by handling, I love this list of verbs that Bill Howe, the director of the eScience Institute, put together. What percentage of your time do you think you spend handling data?
90% of the time.
90? Yeah. So the eScience Institute at UW, they are out of the computer science department, and they consult different domain scientists around campus. And they always ask them this question, and the most frequent answer is 90%. So this is not just in astronomy, this is ubiquitous across science. And so I think we're going to have a lesson on profiling later this week. If you are profiling your code and something's taking 90% of the time, that's where you're going to start your optimization first. So I was hoping to talk about how to decide what data model to fit your data fits into, and also what tools to use. But first, a little thought on tools. Tools come and go, but the concepts behind them are here to stay. So one example is this Git versus SVN. So if you look at the Google trends for this, you'll see that somewhere 2010, 2011, the number of Google searches for Git surpassed that of SVN. And for example, the SDSS project team, the LSST's project team switched to Git around this time. And the reason we did so was because it was becoming more popular, and there's quantifiable benefits to using tools that are more common. You have more community support, there's more answers on Stack Overflow, for example. And so in 10 years, there's going to be we're going to be using something new for version control. But if we understand the concepts behind version control, we're going to be ready for that, and that transition is going to be seamless again. So while focusing on specific implementations and tools and their syntax is fun and you can apply it immediately, learning the concepts behind them is more future-proof for your career. So if parts of this talk seem a little abstract, this is my rationale. So today we're going to be talking about SQL databases in a broader context of data management. I understand that Tomasz would have already discussed SQL databases with you at the first session. And then I also want to talk about SQL in a broader context as an implementation of relational algebra, just to show that there are other implementations of relational algebra that are not SQL databases. You don't always have to load your data into a SQL database to get joins and group bys. And then we're going to discuss indexes and spatial indexes, not only because it helps you get your data out of big databases like SkyServer more efficiently, but it's also a precursor to understanding parallel databases and partitioning your data. So we're going to talk about parallel databases tomorrow. Okay, so first, databases in context of data management in general. So how do we store data? You can think of this many different ways. So physically, we store it on a hard drive. It has the properties that it's non-volatile. That is, you turn the power off and it's still available. The trade-off is that it is orders of magnitude slower to access than memory, and so you have to really optimize your reads and writes to disk. You can also think of this question logically. How do you store your data? What is your data model? Say you have 1 million images from a number of observing runs or surveys that you want to store. You might think, well, I don't need a data model. I can just throw them all in some directory structure on disk. You know better than to put 1 million files into one folder, so you might have a directory structure where you split it into your telescope, what kind of data is it, what kind of, or what field you're observing, and then you can go farther, what dates are your observing runs, and even farther, what filters are you observing with. You can ask questions of this directory structure. For example, how many images were taken with Hypersup Prime Cam in the Cosmos field on March 26th of 2014. So you can do this really easily, and you get an answer back in 40 milliseconds. But what if we change that question to how many images were taken with the HSC wideband? I'm sure there's better ways to do this, but a simple search took 48 minutes when I tried this. And that's because you have to scan through the entire HSC directory to find the directories that are named HSC wideband. So even though you didn't think you had a data model, you were modeling this data as a tree structure. And tree structures have some properties where they're very quick to traverse through the nodes, but anything else, you have to scan through a large portion of the table. So one thing you can do is scan through it once and store all these fields in a table. And it has the same data. You've got your observing date, your field, your pointing, your visit. But now you can quickly search through this table and find all the images that were taken with the HSC wideband in milliseconds yet again. And so tables, we also call these relations, and these are the basis for relational database management systems. They're made up of columns and rows. Rows are also sometimes called records or tuples. And you can also have data that's related to each other. And I was inspired by Cameron's demo this morning using people and astronomers as a as a thing that we want to model. So I was wondering if you guys would find it fun to try to model the same thing but with a relational database instead of object-oriented, because they're very, you can do all the same things, but they're very, very different. And this difference even has a name. It's the object relational impedance mismatch. And the problem comes up frequently when you have an object-oriented application that needs to query a relational database, and people have different ways of handling this. And I originally was going to do this as a demo, but I think since we lost some time, it might be easier just to do it on the board.
Let's do the demo.
Okay.
We'll get the time back.
Okay, let's see. Okay, so we're in a MySQL database right now. And I'm making a new database for us to play around with. Is it, can you guys all see the bottom? I know this is not ideal. I can try to move it up if that helps.
I can see it from the back.
Okay.
I don't want to speak for everyone.
Cool. So I'd like to do the same thing with people, but I want to add a component. So Cameron showed us that object-oriented programming lets you model inheritance, that is, objects that are also objects. We call this relationship we call it ISA. So an astronomer is a person. There's another type of relationship as well, which is composition, which we call has. So astronomers have a publication, which was the example from this morning. This morning we modeled the publications as just an integer to count the number of publications you have, but you can also have a publication object that stores more information about a publication, like its title, its publication date, its journal, and stuff like that. So let's create a person table first. Needs an ID, first name, last name. Anything else you want to add in there for phone?
We did phone number this morning if you want to do that, but
Okay.
maybe I should have not said anything. Sorry.
You wouldn't store a number as an int, because why wouldn't you store a number as an int? So a rule of thumb for storing data as numerical values is if you have to do any math operations on them, and you would never take phone numbers and add them together or multiply them or divide them or anything like that. You don't need that functionality. Okay, let's create a publication. So this is new. What do we want our publications to have? Maybe we should have two fields.
A name?
A name?
Yeah.
Like the title?
Yeah. Year?
What, I didn't hear that.
The journal?
Journal?
The date published.
Mm-hmm.
Yeah.
You have a single bar chart.
Oh, crap. Thanks. I'm just gonna leave it at that. Okay, let's add some data to this. I'm gonna put Cameron first. Yeah, that was not the best way to do that. Okay. I'm gonna put myself in it. Okay, so we had a title. Now in real life, we would definitely not store publication or journals as a random text field because there's a limited number of journals, and you would have a separate lookup table with an ID and formal name for every journal.
The table's called publication.
Yeah. Okay, so we now have our two tables, but people have publications and publications have people. And we want to be able to look up what publications a particular person has published. And we also want to know what the authors of a publication are. So do you guys have any ideas on how to model that in this relational model?
Create a table with the list publication ID and then the list of author IDs.
Yeah. So people sometimes we'll call this person publication. You could also call it something more descriptive like authorship. I think I'll call it authorship. And now we want to connect the people with their publication ID. And normally I would set the IDs of each of these tables as primary keys and also set them as foreign keys in this table, but that is a little.
Can you spend 2 seconds telling us what primary keys and foreign keys are?
I'm going to talk about that later when we start talking about indexing. There are some things you can do to these tables to make the joins and indexing more efficient. It's mostly logical, however, to enforce certain things to happen when you make updates. So, okay, let's insert some data into into authorship. So let's say we are both authors on both papers. How many rows should this table have?
4.
Right.
Mhm.
Every combination. So now let's ask a question of this. How about give me all of the titles of all the papers that Cameron wrote in this database. So what do we have to select from here? And we're going to join on their common key, which is OID. Okay. And now we also have to pull in the person table as well.
Narrative.
Let's just see if this works before we.
I think for publication revisions.
Yeah, you didn't do pub.pub ID.
Right. Thank you. Okay. And now we have every combination of publications and people. So the difference, what are some differences between this and the object model that we used this morning? So if you had a person class, and I'm not going to do this exact in Python, but how would you store the publications that this person had?
Probably have like a list of objects.
Yeah. Exactly. You would have an attribute that was some kind of container. You would have probably a list. We'll call it published. And then you can add publications to this. But the tricky thing here is that it makes it more, finding all the authors of a particular publication with that model is much more difficult. And so what you're doing by using that particular model is you're assuming that you won't have to ask that very often. So we call that aggregate oriented, and there are some databases that are aggregate oriented, like NoSQL databases, which we'll be talking about tomorrow. But they assume that you have some kind of natural way to aggregate. The fun thing about relational databases is that they're fairly assumption free. You can slice and dice your data any way you want without making assumptions ahead of time. Okay, so I said you can usually slice and dice it any way you want without making assumptions ahead of time. That's not always true. And so the case where that's not true is say we have a person table again, but now we want to model the friendships. the way that Facebook would, for example. And the way you would do this in a relational database is you'd have a friendship table with 2 IDs and this row would now record this friendship. And if I were to ask the question, how many friends does Alice have, you can express this in SQL just fine. But if you were to ask how many friends of friends does Alice have, this gets a lot more complicated. And if you want to ask what are all the 3rd-degree connections of Alice, this gets even more, and you find that you end up having to do these recursive queries that get very, very complicated. So relational databases are not good at modeling graph structures. So and graph structures are, some examples are the internet, where you have links to your web page and links away from your web page, social networks, things like that. So if you have a data set that is not fitting into the relational model very well because you have a set of nodes and edges, that's probably because your data is a graph and doesn't fit well into this data structure.
I'm just curious, this is a thing, right? There are also graph databases.
Right.
Do you think there's any sense out of, there's also some that are sort of like hybrid databases. Do you think that makes any sense?
So I know there's graph databases out there. I have never used one, and I have never had a use case come up in astronomy for graph databases.
So someone in my group is working on is it dwarf galaxies that are associated with their central galaxy, and they're doing it as a graph database because they're interested in the relation between the merger trees, basically, of the galaxies. So, just someone to do
because there's an unlimited number of
I think
steps away from.
Because as they evolve, they merge into each other. So I think that's the graphs that they have.
Right. I've seen galaxy merger trees expressed in SQL relational databases as well. That's a cool application. And in the exercise, we also have it looks like a graph structure, but it's not really, because you only care about one step away from each node rather than an unlimited number of steps away from each node. So things to keep in mind when you're deciding what to do with your data is what data model are you going to use? Or do you have a tree, or do you have a relational model with tables, or do you have a graph, or a set of keys and values? And the good thing is also to think about what the constraints are on this. So for example, with a file system, an example of a constraint is that a file can't have more than 2 parent folders, for example. Okay, I understand that you guys learned SQL in the first session, and we reviewed it a couple days ago, or yesterday, right? But you don't need a SQL database to get the power of SQL. SQL is just one implementation of relational algebra, which is algebra on tables. So the same way that regular algebra is operations on scalars, relational algebra is algebra on tables. And regular algebra has a nice property where if you chain operations, you always get a scalar back, which makes it possible to compose operations. The same is true for relational algebra and SQL. No matter what you do, however many operations you have, you always get a table back, which means that you can chain operations. This is just all the familiar selects, joins that you learned already. You also have group bys, aggregates. And we can do this with other tools as well. So one of my favorite tools for getting SQL functionality is pandas, which is basically if R data frames and SQL had a love child. So when I was first, my old job, I used SQL every day. And when I first got to grad school and was learning Python, I mostly used NumPy arrays. And I was finding that I had to write my own functions if I wanted to join NumPy arrays, and I had to write my own functions if I wanted to group by, and I felt like my tools had gotten very blunt. And apparently Wes McKinney was having the same problem. He was a quant on Wall Street using SQL, but also wanting to do analysis in Python as Python was becoming more popular. And he quit his job, lived off his savings for a whole year to write pandas, which I am extremely grateful for. He has, at SciPy a couple years ago, he told the personal story of the birth of pandas, and I put the link here in case you guys wanted to watch it. It's a pretty fun talk. So you might be thinking, oh, but I can only use pandas if my data fits in memory. And that's mostly true, but not always true. So say you have a small table. So this is an actual example from real life. Say you have a small table, which is a list of exposures, and a long table with a list of astronomical objects or sources. This is your photometry. The problem is your photometry table, which is, call it 1 billion rows long, has flux measured in counts, but you really want magnitudes. But to get the magnitudes, you need to pull in the calibration, the 0 points from the exposure table, so you need to do a join. With pandas, you can read in the small table, which is, this is the exposure, the small table with exposures containing the 0 points. Read that into memory and just leave it there. And then when you read in the sources, this is the table that doesn't fit in memory. You can set a chunk size and then iterate over this object, and it'll give you, with every iteration, a full data frame. So if your data can be partitioned by row easily, this is a good way to get around the memory limitation. And sometimes you don't want to go through all the trouble of doing things the most efficient way possible. So when you're deciding what tools to use, I always think about, how many times am I going to do this? Am I going to do it at least once more? So doing things all in memory might take longer, but it's quick to set up. You can use the tools you're familiar with and just go do something else for a day. If I am sure that I'm not going to need to do a task ever again, I have 30 minutes to answer a question, and then that's it. Can't spend any more time on it. I will sometimes use Topcat. Who here's used Topcat? So Topcat also implements relational algebra. It's written specifically for astronomers by Mark Taylor, an astronomer at Bristol. You can tell because you can also do joins not only on numbers, but you can also do joins based on RA and DEC positions, which can even include uncertainties on RA and DEC, which is why you know this was definitely written by an astronomer. So the downside to this is that you close the program and your analysis is all gone. So it's good for very quick but very low overhead tasks that you need to do. And so those are the two that I used. I was partly expecting. I don't know if I have never used AstroPy tables. I don't know if it has join or group by functionality. It does. Okay, so maybe Eric can tell us more about that some other time. Okay, so the last thing I wanted to introduce today is the idea of indexes and parallelization. How far did you guys get on indexes last time?
You mean in session 1?
Yeah. Did you?
Nowhere. I think it's, yeah.
Okay. This concept of scalability comes up a lot, and it means different things to different people. In terms of databases, in the past it has meant practically that it is a process that can function and complete even if your data doesn't fit in memory, and databases accomplish that. But now and looking forward, when people say that something is scalable, they usually mean that it completes even on thousands of cheap computers. So the right-hand side of this chart we're going to talk about tomorrow, and the left-hand side we're going to talk about today in indexes. So algorithmically, we'll say that something's scalable if for n data points it can complete in either n or n squared or maybe n cubed operations. If it takes an exponential function of n operations, we'll say that it is definitely not scalable. Going forward, this has been adapted to mean that it takes no more than a polynomial time n operations, but divided by the number of processors that you have. And you can even take this further, and people will refer to scalable as something that can operate on streaming data, which Gautam's going to tell us about later this week, where you only have one shot at processing the data. You only have one pass at it because it just keeps streaming through. So that would have to complete in n or possibly n log n operations. So we're focusing on this green box for the moment. Okay, so example. Say you have a table with a value that's an integer, say that this is each box is now a row, and we have 20 rows, and we want to find all the rows where this value is equal to 41. How many comparisons would we have to make?
As many as the numbers we can.
Yeah, 20. So it basically scans through. Is 41 equal to 41? Yes, write it out. 72? No. 0? No. 30? No, and on forth. Assuming that you want to do this type of query frequently, what's some pre-processing you can do to this to make this much faster? Yeah. So if you can spend the time initially, the thing to do is to sort this at a time. Now to find all the rows that are 41, what you do is you jump to the center. Is 41 greater than or less than 30? Greater. So then you cut this out, focus on this half, go to the center, we'll say it's here. Is 41 less than or equal to, or less than or greater than 53? It's less than. So then you go to the middle. It's equal to 41, so now you can just step through and return all your values. So this takes log n operations. So what you're doing is you're pre-computing ahead of time to make future lookups faster. In databases, these are implemented as B-tree indexes. It's a collection of keys and then pointers. So you have, we'll step through this same example. Say we're looking for the value 40, the rows with value 41. It'll start at the top of the tree. Is 41 less than or greater than 80? It's less than, so then it'll follow down to this node. It's greater than 20, but less than 60. So then it'll follow the pointer down to this node. It's greater than 40, less than 50, so it'll follow the pointer down to this node. And this, then it'll start searching. But so in this example, there is no 41. These leaves can either be the pages of data themselves, And by page, I mean the 64 kilobyte blocks that databases store their data in. When you make a read from disk, when a database makes a read from disk, it always reads in a full page at a time, which is typically 64 kilobytes, and this is just to make reads faster. Databases usually have a memory buffer pool that is available to it all the time, and it tries to optimize how fast it can read big chunks in. So sometimes these are the data themselves, but sometimes they are pointers to the data. In the case where they're the data themselves, we call it a clustered index. And in the case where they're a pointer to the data, it's an unclustered index. Which one do you think is better? I'll make that more specific. Which ones, if you need to look up a large range of data, which one do you think is better?
Clustered.
Yeah, clustered. Because not only do you have one less step of direction, you also have all the data contiguous in order on disk. So once you get to these pages, you can just step through and pull in the neighboring rows. How many clustered indexes can you have on a table? If you think about clustered indexes as the table itself just sorted, how many? Yeah, you can only have one clustered index on a table because you can only sort your table one way. Something to be careful about is MySQL and SQL Server and Oracle will all automatically create a clustered index on your primary key. There's debate on whether or not this is beneficial, but I'm not going to get into that today. Unclustered indexes are still useful, especially for the case where you need to find small data sets within large data sets. And this is really where databases excel. You can very, very quickly grab one row out of a 50 terabyte database. I mean, it takes milliseconds. And it's through indexes. Here's our source and exposure example again. So we have astronomical sources with an RA, a DEC, a magnitude, and then we have all the information about the exposure was taken from, the filter, the MJD, and a path to the file name. So we're going to be joining these a lot. What do you think would be some good indexes to make on this? A good rule of thumb is that if you're going to be performing joins on a table a lot, is to make an extra cluster or unclustered index on the key that you're going to match to the other key. So pretend we're in MySQL at the moment. We have a primary key here defined on the source ID. And this means that this table is going to be sorted on disk by source ID. Likewise, we have a primary key on exposure table, which means that table is going to be sorted by the exposure ID. Another property of primary keys is that they have to be 100% unique on the table, and this is strictly enforced. And that's why when we define the source table, I included this not null clause here. Okay, so another question. Say there's only 5 different filters in my exposure table. I pretend this is SDSS and I only had UG, RA, and Z available. Do you think it would be beneficial to make an index on filter? So I see some nods, some no's back there. And that's right. The question is, will it do? Another question is, will it do any harm? The reason you don't want to make an index on filter is because for a single filter, you probably only have a whole fifth. Like, say you're looking for filter equals R, up to a fifth of your table will be R. And so if you are seeking all the exposures where filter equals R, you're pulling out a fifth of this table. And so you don't really get any benefit over doing a table scan, because you have to seek through your index. At the end of each seek, you get a pointer to the page that you then read in, and this adds a lot of overhead. So there's a trade-off involved. If you need a very wide range of data back, filters don't help you. So one question is, does making an index hurt you anyway? Some database systems are smart enough to know not to use indexes if they exist, if they won't help you. So Microsoft SQL Server, they store statistics, histograms basically, on all the tables and the data on them, so that they can make more informed decisions on when to use certain indexes. But MySQL, for example, doesn't have the same benefit. And for the LSST project team, we accidentally had a index for filter on one of our tables, and it turned out to be slowing down the queries a lot, because it wasn't smart enough not to use the index, even though it wasn't helpful. But we do small seeks within large data sets very frequently. The sky is huge, and we very often only care about one small part of the sky. We do search cones. We'll search for RA and deck boxes, and we'll also do cross-match queries where we have a set of RA index from one database, and we'll want to pull in the best matches from another database. So this is a great use for indexes. However, we're interested in both RA and deck. So what would you index your table on to do a spatial seek? You can. So you can index on RA and deck. This won't help in this particular case, however, because RA is a float. And when you sort by two values, it'll sort the first value, and then anytime the first value, you'll have two or more rows that are the same, then it'll sort by the second value. And so if you have a pile of floats, you really are only sorting by RA. This problem comes up all the time in industry if you just replace RA and deck with latitude and longitude. For example, Uber, every time you make a ride request, Uber will find all the cars that are closest to you. A lot of databases have spatial support. I've used PostGIS, which I like and have found appropriate for astronomy data because you can define a perfect sphere. Microsoft SQL Server geospatial support was not helpful because so most of these databases, they have a oblate model of the Earth because the Earth is not a perfect sphere. But most of them allow you to plug in a perfect sphere that would be appropriate for astronomy. SQL Server, on the other hand, does not. You get the Earth, the best model we have for the Earth, and that's it. So because the math, is that a question?
No, I was just wondering why they would do that.
I asked on a forum and got a snarky answer. I wondered the same thing. Okay, so this is why I don't like putting talks on YouTube. I'm gonna clip this out. The math on perfect spheres is actually a lot easier than on the Earth. So astronomers like writing their own implementations of things also. So a common one that you'll find is hierarchical triangular mesh, which was used in Sky Server, SDSS, for example. The idea is very simple. You split up a sphere into increasingly smaller triangles. Each triangle has a center with an Aryan deck, and the goal is to reduce this Aryan deck of each triangle into one integer, which you can then index. We number the triangles using a space-filling curve, which has the nice property that numbers that are close in integer space are also close to each other on this sphere. We are going to do a demo of this too. So we're going to use this in LSST QServe, probably the LSST database. It's also used in Sky Server. I'm going to show you the specific implementation in our prototype MySQL database. However, don't memorize the syntax because you probably won't use this. It's just for illustration purposes. The exercise that we're going to do after the break will have a simpler example that you can run on Sky Server, for example. So I'm connecting to an LSST development database at NCSA. Sorry. And what I'm going to do is call this function. So I'm looking for all the sources within 6 arc seconds, 3 arc seconds of this coordinate. There's this function called S2 circle region, which will create a table called SciSQL region, which has a list of HTMID ranges covering this search circle, which is centered on that Aryan deck that we're looking for. The 20 here is the size of the triangle in the hierarchical triangular mesh. So this is something you want to keep constant within your database. This is the distance from your search center in degrees. Yeah. Okay, so if we print what this table creates, you'll see that what that function call creates. It creates a table with a series of ranges of HTMIDs, and these HTMIDs will cover that search region. Now, we have pre-computed the HTMID for every source in our source table. And so now we can join on this HTML range table where HTMID is between the minimum and the maximum. And these are the results. We're not done yet, however. Are there any questions on this query? We're selecting from just a giant table of sources with coordinates and photometry like we were over. Okay, there's more objects in this return set than we want because the HTMID ranges are guaranteed to cover your search area, but they're not an exact representation of your search area. You need to do an additional search. And that is guaranteeing that the object, the ARIA index of the object, is within 0.05 degrees of the search ARIA index that we specified at the beginning. So this function will return true if the source is within this distance, and it will return false if it's not. So requiring see this. See, I may have had a mistake, which is still completed. Okay, with that, so with this extra criteria, I'm plotting the results with the extra criteria in black and the original just the join on the HTML ID in white. So you can see that your pre-filtering was pretty close to the original circle. So the goal is to really minimize the number of times you have to calculate this distance to your search area. And this hierarchical triangular mesh does that. Okay, and one last point I wanted to make is you notice that I don't pass in the ARIA index into my query string. You guys probably guessed why that is. But if you're writing code that only lives on your computer, it's not that important. But if you're sharing code and sharing databases, you definitely want to use the functionality made available by your database driver and not pass in any data into your actual query string. Okay. The last thing I want to talk about before we start on the exercise is some background on the challenge problem and the data set that you're using in the exercise. So the little data file that you'll be downloading is the photometry that's been measured on this image here. Every white point on this image is going to be a row in your table. This photometry was measured using a deep blending algorithm. That is, it found all the pixels that were above some threshold, but these are oftentimes many sources overlapped. It will then split this footprint into many sources. And say you have 5 galaxies that are overlapping. It'll keep the 5 galaxies in the database, but then add 5 separate, so it'll have the parent, the whole footprint, as a row, and then it'll also put the 5 separate galaxies as 5 more rows. These 5 rows will be marked primary, and the parents will be marked not primary, as an indication that you shouldn't use that row. So what we're going to do is join a table on itself to find information about these deblender children's parent. And in the challenge problem, we can use this information to compute some survey area just based on the catalog itself. What we're going to do here is compute a Delaney triangulation and then put every one of these edges into a database or into a data frame and try to select which edges appear once and which edges appear twice. The edges that appear twice will be a member of a triangle, and the edges that appear once are going to be on the edges. And there's this nice package called Shapely, which will take So so once you compute which ones have one edge, you can throw this into Shapely, and it'll actually compute the area for you of everything inside these edges. So just some background on that. Okay, so I'll let you guys take a break and get started.
Sorry, we're not taking a break, but first let's thank Yusra.